Okay, so today we're going to look at the concurrent support in FS2. So here we're in Ammonite. Let's go ahead and load FS2 090 M3. That's the latest milestone. And let's get a bunch of imports out of the way. So I'm going to import everything in the FS2 package, and I want to import the task data type that we looked at last time, the time before. I also want to import duration syntax from Scala concurrent because we want to do some stuff with time. And one of the first combinators I want to look at today is this logging combinator. So if we take a look at this, I have this method here called log. Log takes a prefix string as an argument and returns us a pipe from A to A. Recall that a pipe is really just a function from stream task A here to stream task A there. And so because a pipe is just a function, we define that we just grab the input stream here and call eval map. And on each individual A that we get passed to our function, we're just going to print something to the console. We're going to print the A to the console. And then we'll return our A immediately. So with this combinator, we'll be able to watch elements as they're pulled through our stream. So let's use it real quick. Let's say we have the stream 1, 2, 3, and we feed that through log. And for now, let's just use no prefix. And then we can just run that. Remember, that's going to give us a task back. And if we were to run that task, you can see that the only thing that's occurring here are the print lines as those elements got pulled, but there was no output coming out of our particular stream there. And of course, we can add arbitrary prefixes, like we wanted to call this stream A, and run it. You know, we can get that output. Okay, so that's the first combinator I wanted to look at. And we're going to use this a lot today because what we're going to do is build up some concurrent streams and print out as elements are being pulled through all these different streams concurrently. And we'll get some idea at the console as to the order of evaluation of things that are occurring. Okay, the next combinator I want to build is one that's kind of strange. I have this one called random delays. And the idea with random delays is that it's also going to return us a pipe of task AA. And it's also going to, by the way, call eval map on each individual element in our stream. But what we're going to do is add a random time delay to the emission of each element we get. So let's look at how this is implemented. We take the max time delay as a finite duration. And then we say for each element we get here, the input element A, let's calculate a random time delay from 0 milliseconds up to the maximum milliseconds specified. And then let's return a task. So delay here is a task, task of the number of milliseconds to delay. So we flat map on that, and we return this task here. So this task, task.now of A, is going to give us our input value again. But then we schedule its completion, its execution for d milliseconds into the future. So let's try to use this random delays function and see what we get. Oh, we need to just set up some implicits here. So here's our strategy. We'll use a thread pool of 8 threads, and our scheduler. We'll use a thread pool of 4 threads. Okay. So we have our random delays function. So now let's take a stream. Let's say we have a range stream, 1 to 20. And remember, range on stream works just like, well, let's just look at it. It starts at the first element and increments by 1 until we get to the second element. So let's take our range stream and feed it through random delays. And we'll say the maximum delay would be 1 second. Now, if we were just to say dot run here, we're not going to see any output. And if we were to say dot run log, what we're going to end up with is a task that when executed is going to give us a vector of the numbers 1 through 20. But the execution of that task is going to take something less than 20 seconds, but more than we want to sit. So before we do run or run log, instead I want to use our log combinator to see the values as they're emitted. Okay. So if we do this, you can see that each element that's being pulled from that stream.range is getting delayed for some amount of milliseconds. We see the delayed prefix we use is put in front of each of those values. And we get a good feel for the way random delays is working. If we were to put another log on the front side of random delays, you can see that we're pulling those elements as we need them from that input stream. Right, so the time here, we're always blocked here in this before delay. Okay, so the reason I wanted to start with this particular example is that our random delays function uses this schedule combinator on task to complete this task at some point in the future. It's really important, though, that while we're waiting for that task to execute in the future, we are not blocking a thread in the thread pool that's backing our strategy. We're not blocking a thread in the scheduler that we have. And so this is an important concept in FS2. We have this stream that's being pulled through random delays. It's got this concurrent behavior where it's got things that are executing in the future. And so the stream itself is semantically blocking in the sense that we're waiting for this task to complete before we go ahead and pull the next element from our input stream. But we're not actually physically blocking a thread in our runtime environment. So a lot of the times in FS2, when we talk about different combinators that may be blocking, we're always talking about semantic blocking. We're never talking about literal thread blocking. Okay, so let's simplify our example a little bit. We're going to start, I want to get the stream for this stream.range call. And I'm going to name this stream, rather than calling it delayed, I just want to call it A. And let's give us less elements so we don't have to wait so long. So val A here is a stream of task comma int. And if we were to run that, we get the same output. I want to do the same thing now with another stream. We'll just call it B. Okay. And so we've seen a few ways that we can both deterministically and non-deterministically combine these streams. Right? We looked at pipe twos, a way to open two different streams and then pull elements from either one or both. So let's take a quick look at those again, this time using some of our new combinators. So the first one I want to start with is interleave. So if we interleave A and B together, if you recall the way interleave works is that it's going to pull an element from the first stream, and then it'll switch and pull an element from the second stream and go back to the first and keep alternating, right? So I'm going to interleave A and B together. That's going to give me a stream of task comma int. And then I want to log the output. And then we can just execute the stream and see what happens. Okay, so we can sort of get a feel for what's happening here. We wait for an element from the A stream. Once we get it, we wait for an element from the B stream. And then we're outputting both of those elements into the output stream. So there's this kind of interesting behavior where we're going back and forth and then only emitting elements after we've gotten both a left value and a right value. Recall that the output, like when we interleaved A and B, we had a stream of task of int. And we're not seeing these output ints come out until we have an element from both A and from B. So instead of interleaving, what if we just want to emit an element as soon as it's available from either A or B? We saw the merge pipe 2, where we can just merge non-deterministically from either of the two inputs. So if we were to run the same example with merge, actually let's go back to our example. So let's run this same thing with merge now. You can see as soon as an element's available, regardless of which side it's coming through, we emit it. And we don't have like this alternating behavior where we go from A to B to A to B. Instead, we have elements come out, or elements are pulled from the source streams as soon as they're available. Right, so like in this particular case here, we had 2 elements from A come out back to back. Down here, we had 2 elements from B come out back to back. And so in this merge case, what we're actually doing is asynchronously pulling from both of our input streams, both A and B. And then both of those input streams are semantically blocking on that schedule call. And then one of them happens to finish first, so we emit that value. Then we go back and say, give me your next value. So we do another task.schedule. And that subsequent task.schedule may execute before the outstanding schedule on the B side. So merge is one of the simplest ways to do concurrency with FS2. And if we were to look again at the output of the output type of A merge B, we can see that it requires both streams to be of the same type here. So we merge a stream of task int with a stream of task int, we get back a stream of task int. And so there's sort of arbitrarily, or maybe not arbitrarily, but there's a lot of different small deltas to this pattern that overall are built on the same underlying asynchronous merging behavior. So for example, we have A either B. A either B is going to behave just like A merge B, but we're going to remember what side an element came from. Right, so if we got an element from the left side of merge, then what we get on the output side is a left int. If we got an element from the right side of merge, we'll get a right int. So let's do a quick example of that. Right, so we can see these lefts and rights coming out. We get to track where those elements came from. The other nice thing about either is that now our stream types don't have to match. So if A was a stream of task int, but B was a stream of like task string, by using the either combinator, we not only remember which side it came from, but now we have those unique types in the 2 branches that we can track and then transform with our normal combinators like map and filter and so forth. Okay. So what happens if we have a C? All right, we have A and B, but let's say we have a C here. Okay, so now we have stream A, B, and C, and we want to merge all three of them together. One way to do this would just to do pairwise merges. And that certainly works okay if we have 2 or 3 or 4 elements. But what if we don't know how many elements we have? So for example, we could have a stream of streams. So a stream of streams might look something like this. The elements in our stream are again streams, and maybe they're stream events. Okay. Now our stream of streams maybe represents something like the inner stream here is a file we want to read, and the outer stream is a stream of like all possible files that might exist in a directory over time. Or the inner stream represents a TCP connection to a server, or from a client to our server. And the outer stream represents each individual client that connects to our server. So how would we go about sort of flattening, if you will, this stream of streams into a single stream, and still be able to do the types of things we were doing with merge? So in FS2 we have a combinator for this. It's in the concurrent package. It's called join. The join combinator, you can see, takes 2 argument lists, each of 1 parameter. The first argument is the maximum number of streams we ever want to be open at any given point in time. So this is sort of like a parallelism factor, right? Like how many of these inner streams should we ever be processing in parallel? If our outer stream represents like all connections to a server, then our max open is going to be like the maximum number of connections we want to multiplex over at any given point in time. Right, so let's start here and say, with our example, let's say we want to be processing 3 at once. And then our second parameter list takes this outer parameter, which is our stream of streams, and here we can do that, we can just pass our streams parameter. So you can see that what we get back is sort of like the flattened stream, if you will. So we took a stream of stream events, and we got back a stream event, right? So it's sort of like flattened from collections. But there's this runtime behavior that as we pull elements from it, it's only ever going to open 3 of our streams in parallel. So let me do some examples because I think it'll help. Actually, let's log the output here. All right, so remember in this first case, we're going to say 3 streams can be opened in parallel, but our streams collection here, or the outer stream, is just a list of 3 streams. So this should have the same behavior effectively as like merging all 3 in parallel with each other. And we can see that, right? We see output from A, B, and C all coming out at the same time. So what if we changed our definition of streams here a bit? Let's say we're going to generate our inner streams dynamically. So we'll define this to say stream.range, and maybe we say 1 to 10. And now we want to, so this number is going to represent like, you know, an identifier of the inner stream. So now we're going to say for each of those numbers, we want to turn them into a full stream. So we'll map over this and say for each identifier, we want to create a new, let's create a new stream.range 1 to 10. Let's put that through random delays over 1 second. And we'll put that through a log function. And to log it, let's just take the letter A and add the ID to it. And we should be good. So we'll, actually, let's change this a little bit. I want to start at 0 instead of the outer stream. I want to start at 0 instead of starting at 1. Okay, so now if we were just to, well, so now what we have is this stream of streams, and each stream is going to have the output. The first one will be named A, the second one will be named B, the third will be named C, and so forth. So if we concurrently join the same, using the same code, we're going to join the streams collection, but we're still only going to allow 3 streams to be open at any given time. What we see, right now you can see like 65, 66, 67 is all open in parallel, but you can see gradually the streams with smaller IDs, the inner streams with smaller IDs finish and new streams are open, right? So right now we're up to like 71, 72, 73, and soon that'll finish. Right now we're up to 72, 73, 74. If we were to do that again with the right conversion from integer back to characters, we get our letters here, right? So here we have A, B, and C open, and soon A looks like C finished first, so then D got open next, right, and so forth. Okay. So concurrent join lets us do these type of multiplexing of processing, and do so in a way where we can guard how many streams we run in parallel. All right, so I'd like to now look at some data structures that help us build concurrent features when things like just using merge and other pipe 2s aren't sufficient. So the first thing I want to look at is the signal data type in the async package. So let me switch over to signal. And actually I want to open async first. So the async package in FS2, oh, and actually a side note about FS2 code organization. All of the package objects, they're, rather than being defined in like a package.scala file, they're defined in a Scala file which matches their package name. So for example, here we're looking at the async package that's in the async.scala file. If we wanted to look at like the TCP package, we look at the tcp.scala file, and you can see it's a package object TCP in the fs2.io package. So as you navigate the FS2 code base, just be aware that the package objects are not defined in package.scala files, but rather in a Scala file whose name matches the package name. Okay, but yeah, so I want to look at the async package, and we're going to start with this concept of a signal. The async package, the primary interface to it is through this package object, and the package object is going to provide us a bunch of different constructors for creating different concurrent data types. So the first one we're going to look at is signal of. And so you can see signal of requires some type constructor f. We pass it an initial value, and it gives us an f of a signal of that value. And if we look at signal, we can see signal is split up into two interfaces. The trait itself extends an immutable signal trait. So I want to start there. You can see that an immutable signal just represents sort of like a cell in memory, like an atomic reference almost, for a single value of type A. And in order to read values of that type A, we have to do it inside this F effect. So how could we, what's the mechanism for actually doing these memory reads? We have a bunch. The simplest here is at the bottom. We can get a value out of our signal. But in order to get a value, we actually get that value inside an effect. So normally when we're working with signals, or at least getting started with the library, our effect type is going to be task. And so if we wanted to read a value out of a signal task comma int, we're going to get back, when we call get, a task event, right? Something that still has to be evaluated at some point. It still has to be interpreted and actually executed. There's also a bunch of other interesting methods here on immutable signal. We have discrete and continuous. And we're going to look at these in the REPL in a moment. But the general idea is that we can register or listen to a signal for changes. Or at least that's what our discrete stream will do. So each time the signal has been changed, we'll get an element put into our stream. Alternatively, we have this continuous stream, which basically says anytime someone tries to pull an element through this stream, just give it the current value of the signal. Right? So there's continuous is always, always, always going to have values. If you were to create a signal and hook the continuous stream up from that signal, hook that up to run log, you'll just run out of memory, right? Because we're always going to have values in a continuous signal. All right, so let's take a look at how to use this stuff. So let's again use integers. So we're going to create a signal. We're going to use the task effect type, and we're going to use int as our value type. And let's initialize it to the value 1. You can see what we get back as a task. So we have a task that's wrapping our signal. We can't, we don't just get a signal immediately. We have to evaluate this task in order to do something with it. So while we could call x.unsafe_run to sort of, cause the evaluation to occur and then let us operate on that signal, doing so is unsafe, right? We don't want to be evaluating tasks in the middle of a program. So how can we operate with this? Well, one thing we could do is just call x.flatMap. Now, if we do that, we've got some signal here, x1, and we can do something with it, right? So, for example, so to be clear, this is a signal now of task comma int, right? So what do we want to do with x1? Well, we could just say x1.get, and now we have a task event. Right, and we have that because x1.get, this get here was returning remember it returned us the value of the signal inside of our effect type. So if we were to run this particular value, we're going to get back the value 1. But normally this is not what we want to do, right? Normally we want to work with these signals in some concurrent way. Perhaps we have two streams, one that's one that is reading from some network source and then writing values to a signal. We have some other stream executing concurrently that perhaps is reading from that signal and doing something with the output. So what other ways do we have to kind of get access to this X, to this signal? Another way we have to do it is we could call stream.eval. So if we call stream.eval on X, we're saying convert this task of signal into a stream of task comma signal. So this stream is just going to be a single element stream, right? And if we were to run it, you'd see we'd only ever get one element out, right? We get a single element in this vector. The reason we might want to do stream.eval is so we can flat map on it. And now we have a signal here. X, this inner X here is going to be of type signal. We can do something now with that signal and return an overall a stream. So this pattern of like create a signal, evaluate it, flat map on it, and then return some complicated stream that uses that signal is pretty common. So, for example, let's do x dot discrete. Let's just start with x dot discrete. So if we, if we return x dot discrete, what we're saying is create our signal, and then immediately return a stream of all of the changes, if you will, all of the values that ever get written to this signal. If we were to run this, it's not going to do what we might think it does. But let's go ahead and try anyway. So what I want to do, let's say we're going to take the output of this and run it through our log function. We'll have every output come out, get prefixed with the string first signal. And then I want to run it. But I don't want to just block the REPL because this is going to run forever. So what I'm going to do is just run it as a Scala concurrent future. Okay. So you can see when I kick that off asynchronously, we had the first element come out, this first signal 1. So x.discrete gives us a stream, and that stream is going to be initialized with whatever value is in the signal at the time that this stream starts getting evaluated. So we see our first value come out of it. So how can we make more values come out of it? How can we change the value that's in this like mutable memory cell? Let's take a look at the companion trait in the mutable package. So what we've looked at so far is the FS2 async immutable signal, but there's a mutable signal as well. And what we have, is this type, is the mutable signal type. So in addition to the immutable API, we also get the following 3 methods. And the one we care about right now is this set. So the idea of set is you give it a pure value of type A, and it'll give us back an effect, an f of unit. An effect that, when this effect is evaluated, it has the effect that this value A is put into this mutable memory cell. So let's try it. We have X. We could flat map on X. And now inside of here, we could call set. And maybe we just want to set it to the number 2. And that's going to return us a task of unit. And since we're starting with a task and flat mapping on it out here, what we end up with overall is a task of unit. So that seems fine. And if we were to run this task, you can see it executes, there's no exceptions, but we don't see any output. We don't see another line coming from our running stream up here, this thing that we kicked off asynchronously and it's just monitoring all changes to our signal. And the reason we don't see that is that our value x, remember, is a signal that's wrapped in this task constructor. Or at least type-wise, it's a task constructor with a mutable signal inside of it. But such reasoning actually leads us to a bad place, right? If we think of this as like a signal that's been allocated, a mutable memory cell that's been allocated, which happens to be wrapped in a task, then we're led to believe that when we did this execution right here, where we set this value 2 into that mutable memory cell, that this stream up here should have seen it. So that's a bad intuition. Let's think about tasks in general. When we look at tasks, they're not used to wrap values, right? A task doesn't wrap a value, and a task doesn't wrap like a future value that may be generated asynchronously. Rather, a task describes a computation, describes a way to generate such a value. And so in effect, what we've done in this example is we've executed the creation of this mutable memory cell twice. We created that memory cell up here when we did a stream.eval, and then we created a new distinct memory cell down here when we executed this one. So we have two different memory cells, and hence, why writes to the second one aren't being seen by reads from the first one. So how could we fix this? Well, first, let's just cheat. Let's see if our newfound understanding is correct. In order to do that, let's just not worry about our rule of avoiding unsafe run. Let's just run x right away. So if we run x right away, we now have our signal. So now we can start up our monitor process. The monitor process can be much simpler now. We don't want to evaluate x because we've already created our signal. And hence, this could be as simple as just saying, use the discrete stream off of our signal, log everything that comes through it, and run it all asynchronously. Okay. So if we kick this off, we see second signal output our first value of 1. Now if we say s.set2, you can see we still have no output because we haven't evaluated our task yet. But if we were to take that s.set2 and evaluate it, you can see our second signal monitor is executing in the background. And if we were to execute it again, you can see our discrete stream is going to signal us on every write. Not changes to the value, but on every write to the value. Okay. We could use modify on signals. So if we use modify, you can see what we get back is a async change of int. And if we were to evaluate that, you can see our value did increment, right? It was 4 here, it incremented to 5 here, and we get back, as a result of evaluating it, this change object, which tells us the old value is 4 and the new value is 5. Okay, while we're here, while we're in this sort of cheating mode of running our tasks unsafely, let's experiment with continuous signals as well. So we have s.continuous, and let's just take 100 elements from our signal. You can see I said take 100 elements and then run log, So collect up all those 100 elements, and then go off and evaluate it. And we got back a vector of 100 elements immediately. So continuous signals always have a value. Always, always, always have a value. If we were to say s.set 6, run this continuous take again, we get all of those elements immediately. And you can see, like, as we're doing like s.set 6, this monitor's still running off in the background. And that monitor is not physically blocking a thread. If we were to run like JStack on the Ammonite process here, you would see that there are no threads in our strategy dedicated to this monitor. So even though semantically, you know, we are saying like take each individual element and print it out as it comes out of this signal, semantically it's blocking, but as far as like resource usage is concerned, you know, we're not actually doing any type of thread pinning or thread utilization. Okay, so how can we do things with signals without going into this unsafe run case and still be able to manipulate them in some interesting way? So let's go back. Here is our attempt earlier. We said let's evaluate x, or actually let's just inline our signal creation at this point. So let's create a signal in stream.eval. We'll start it at 0 this time. Okay, so we're going to evaluate this signal. And now we're inside of a flat map call, and we have our mutable signal. And so let's say we want to do, you know, we want to do two things with a signal. One is we want to be able to read from it and print things out. And then two, we might want to write some values to it. So in order to write the values, let's say we take, well, actually, let's create our monitor first. Let's read our values first. So we're going to take s.discrete, and let's put that through our log. And we'll just call that our monitor. And let's think about what type our monitor is going to be. S.discrete is going to give us a stream of task comma int. Through log is not going to change that at all. It's going to print it out, but it's going to return each individual value. So really what we have here right now is a stream of task comma int. Now, our monitor task, we don't really care to do anything with these ints that come out. So why don't we change this to a stream of nothing to be clear that we're not going to use this output at all. And now that won't compile quite as is. In order to get a stream of task nothing from what we have, let's just drain our stream. So draining the stream is going to have the effect of like the stream is going to get run, it is going to be executing, but we're never going to actually output any of the things that come out of it. Okay? So there's our monitor. Now we want to write to our signal. So let's do that. And let's come back to the type. But how are we going to write to our signal? Well, why don't we take one of the streams we used earlier, like let's say the range stream, let's say starting at 10, ending at 20. And let's feed that through our random delays again, over a second each, you know, up to a second each. And let's just call that data for a moment. So our data is going to be a stream of task comma int. So how are we going to write our data to our signal? We can use eval map. So for each, let's say each element in our data, D, we want to say s.set D. So we can do eval map, right? Because s.set is going to return us an f of unit, a task of unit. And we're using eval map, so that task is evaluated synchronously as part of this stream evaluation. Okay. And we'll call this our writer. So what's the type of writer? Well, we've got a stream of task again. And now our data type is going to be whatever the inner type is of this task here, which is unit. Okay. So we need to return a stream at this point, right? Because we're still inside of this flat map call right here. So we're saying, given this signal, we want to return a stream. And so what's the stream going to do? Well, what we would like to do is run the monitor asynchronously, or run it concurrently with the writer that's running. If we were just to say like monitor ++ writer, right, where we just concatenate the two streams together, what would happen in this case is that we'll get the first value, 0, to come out, and then we'll get nothing else to come out, because this monitor stream is infinite. This monitor stream we're never going to reach the end of, because it's just the discrete stream of values in that memory cell. So we don't really want to append these elements. We want to evaluate this concurrently with evaluating that. And we've seen how to do that already by using the merge function. So we can merge the monitor with the writer. And now we're just going to execute those two streams concurrently whenever this overall stream is evaluated. Okay. So if we were to run that, you can see we get the initial output 0 from our stream, and then we start getting the asynchronous updates occurring. And now note, when it reaches the end, we've hung. Right? We've reached up to 20, and we've called unsafe run, and now we seem to be hung. And so what's happened? Well, we merged monitor and writer. Writer itself, let's look at it. Is this a finite or infinite stream? Well, it's just calling eval map on data. And as long as these tasks actually execute pretty quickly, then this will end, this overall stream writer will end when data ends. Or more precisely, the stream writer is going to end whenever the s.set effect finishes executing on the last element that we pulled from data. And then when's data going to end? Well, data is a finite stream, 10 to 20, that as long as you're pulling from it, at worst case, it's going to be, about 20 seconds. So both data and writer are finite, and both of them will end within 20 seconds or so. But monitor, remember, is infinite. And so when we merge the infinite stream with the finite stream, everything worked fine. The writer finished, but now we're still reading from this monitor stream that's never going to finish. And so now we're hung. So how can we fix that? The general idea is that we want to halt when writer halts. And there's this function built in called merge halt both, which says when either of the two sides halts, we're going to halt the entire, or the resulting stream. The default behavior of merge is that it's going to merge when, it'll terminate the resulting stream when both of the input streams halt. But here, we want to say halt both when either of them terminate. So if we run this particular program, oops. you'll see it terminate when it prints 19. Okay. So what are signals, right? We saw this notion. It's this memory cell, if you will, that's created. It has a single value of type A, and we have ways to read and write that value. Those read and writes can occur asynchronously or concurrently, and by using things like stream.eval and eval map, we can do this semantic blocking, waiting for values or what have you. But it's important that we remember that signals really just represent a single memory cell. That's fine sometimes, but what if we wanted to deal with, like, in queuing values, where we have maybe a stream that's producing particular values, we've got another stream that wants to read those values, and we want to put a queue between the two, the output of the first stream and the input to the second stream. We couldn't use a signal, or at least we can't use a signal for that very easily, because a signal just represents a single individual value. So we could start with a signal and then start, like, building up to something bigger. But in order to get, like, that NQ, DQ semantics correct, we would need some type of concurrency primitives. And so that notion is the next thing I want to look at. It's the notion of queues, and specifically bounded queues. So let's go back to our async package. I'm going to skip semaphores as a side note. Semaphore is the next type in our async package. These work very much like semaphores from, like, pthreads or Java util concurrent. They're initialized with a count, and you can increment and decrement the count. Unlike, let's say, a semaphore from Java util concurrent, these semaphores are all built on top of this notion of semantic blocking. So, like, if you go to decrement the semaphore and there's no permits available, you get back, like, an effective unit, some f of unit, like a task of unit. When you evaluate that task, it's going to semantically block until a permit becomes available. But again, a thread is not going to be blocked while that's happening. But anyway, so semaphores are built in. We're not going to look at them today. But if we take the notion of a semaphore and we take the signal that we looked at, we put them together in sort of a clever way, we can start building these bounded queues. So let's look at a bounded queue. Bounded queues look very similar to signals when we look at the types, right? The constructor here, we tell it the maximum number of elements we want to put in the queue. We tell it what effect type we want to do our evaluations in, and what the element type is in the queue. What we get back is like a task of our queue. Let's take a look at the definition of queue. So a queue here has a bunch of operations. The primitive operations are in Q1, which says, given a single pure value of type A, I'll give you back some f of unit that when you evaluate this f of unit, this value A is going to get enqueued. And the other primitive operation is dq1 over here. dq1 just says, it's sort of like our get from signal. It says, you call this, you get back an f of A, and when you evaluate that f of A, we'll remove one element from the queue and give it to you. Both nq1 and dq1 return effectful values, right? Return f of unit and f of A. And then both of them have ways to be lifted into streams. So we can look at the output. We can dequeue all elements from a queue forever. We get an infinite stream of elements that are flowing out of a queue just by evaluating dq1 over and over and over and over and over. All right, so you can see the implementation of this dequeue method is defined directly in line here. And in the same way, we can feed a stream into a queue just by eval mapping nq1 over each individual element. And what's really neat here about the way these signatures end up working out is that, like, when we go to nq an element, we get back this f of unit. When this f of unit is evaluated, it's not going to complete until this value a was successfully put into the queue. So what that means is that the queue is currently full, there's not enough space for this value a, then this f of unit is going to be semantically blocking, waiting for some space to open up in the queue. And there's a similar behavior on the DQ side, which is that if you call DQ1, we're semantically going to block, waiting for an element to become available in the queue. And hence we can just continue to call DQ1, like in this repeat eval case, without blocking any threads. So let's do a quick example with queues. In this particular example, I'm just going to change from using a signal to using a bounded queue. So here we're going to use a bounded queue of 5 elements. So at any given point in time, the queue may have up to 5 values. And then let's change the code quite a bit. So rather than taking a discrete stream from our signal, let's take our queue and use the DQ stream. So we're going to DQ all the individual integers out of this queue, and for each one of them, we're going to log them. Our data remains the same. We'll just have the numbers 10 through 20. And then we could either say eval map q.nq one element of D, which would be fine. But this particular pattern is built into queues. We don't have to write it this way. We could just write data.to q.nq, right? Because q.nq is a sync, so we can use the to method to send all the elements from our data stream into our queue. Oh, and then I'm going to change our logging. Okay. And so what we end up with is output very similar to before. What's a little different, though, is if we were to take this signal example, and let's say our data becomes available very, 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 very quickly. Right? Here we had this random delay on each individual data element. Let's just temporarily remove that. Let's run our signal example such that everything is very, very, very quickly available. And that was not quick enough. But if we were to do it quick enough, you would see that the signal example has the opportunity to have multiple sets occur to the signal, where the monitor will only see the last value. So this particular output looks like that's not happening. It looks like we're always getting, for every value we write to the signal, we're getting an immediate read. But that's sort of luck in this case based off of the CPU scheduling of this particular example. With our queue, instead, we're guaranteed that property. Right? We're guaranteed that for every element we put in, someone is going to have to take that particular element back out. And so I think I'm going to stop here for today. But the async package in FS2 has a lot of additional data structures that are interesting. We did talk a little bit about semaphore, but if you want to look at the details of that, semaphore in FS2 is how a lot of these higher level data structures are implemented. There is a topic data structure. So you could say async topic of task comma int. And what a topic is that it provides a way to do publish and subscribe, where you can have as many publishers as you want and as many consumers as you want. Each consumer that subscribes to a given topic gets its own bounded queue. And then as long as all of your consumers are keeping up, everything runs successfully. But if one or more of your consumers falls so far behind that their bounded queue ends up getting full, then back pressure ends up getting applied to the producers of data. Again, you can create topics directly from the async package. So do explore the different parts of the async package in FS2. And if there's any questions, I'll take them now. All right, thanks for coming.